Hi everybody, today we've got our lesson on comparing two sample means and ultimately two population means. Oftentimes in statistics it might be useful to look at just one population and try to infer about that one population, but oftentimes when it comes to experiments and other sorts of things with statistics, we actually want to compare two populations to one another. So for example, we might want to compare between girls and boys at a particular school who has a higher average or mean GPA. That's a really common example. We're going to talk about more in depth why we might want to compare two means in this video. Whether you realize it or not, we have actually done quite a lot of comparing of two populations to one another already. And this started all the way back in Unit 1, back in September, when we talked about comparing two distributions. If you remember SOX, shape, outlier, center, spread, that's exactly what we were doing with two distributions. So at that point, we weren't quite as advanced in our methods that we could use, but we were still able to compare two distributions based on their graph. So in this case, we have two box plots and we can compare their shape, outlier, centers, and spreads. What we're going to see from here on out in this chapter is how we can get much more specific in our comparison of two groups. So once we have examined side-by-side box plots, we can actually turn that comparison into a comparison or test or interval of two means. So let's say that the two previous box plots were the duration of length of life for two batteries. We have the name brand and then the store brand batteries. When it comes to comparing the two, we could actually compare maybe the average duration of life for each type of battery. And comparing two means is really not that different from comparing two proportions. Before we had P1 minus P2, that was our parameter of interest, the difference of the two proportions. For a two mean tester interval, our parameter of interest is the difference between the two means. So mu1, that's the mean from our first sample, and mu2, that's our mean from our second group. Just like before, when we were talking about the standard error and standard deviation for one sample, we have the same sort of formula for two means that we're going to be comparing. So really, we never truly know what the population standard deviation is. So that's what that sigma is in the first formula here, when we have sigma 1 squared and sigma 2 squared. So what we do to kind of best estimate that is use what's called the standard error, SE, instead of ST, which is standard deviation. And really what that means is we're going to take our first sample standard deviation and square it, divide it by the first sample size, add that to our second standard deviation from our sample and square it, and divide that by our second sample size. So when it comes to creating the confidence interval, this is the part that comes after the T star value, that critical value. And the combination of standard error and our T star is what we call margin of error. As you'll recall in phantoms, or when we're doing a hypothesis test, the T in phantom stands for find a test statistic. And we have seen already that the calculator is going to do all that work for us. So this is just the formula behind that. Again, we won't actually use this because the calculator is going to provide that number for us. But if you're curious, this is what that formula or what the calculator does for you as a formula automatically. The good news is that our assumptions and conditions are exactly the same as what we had before. So the only difference is that we actually have to compare and check these assumptions for both of our samples, okay? So the first one, of course, is that each sample has to be randomly selected or at least be a representative sample. And often that's going to be stated right within the problem. We also have the 10% condition. And what we need to know there is, are each of our sample sizes less than 10% of our population size? And the key thing with a two sample tester interval is that the two sample sizes are not necessarily going to be the same. Sometimes they will be, but they don't absolutely have to be in order to do the procedure. Okay, so check that 10% condition for each of our samples. Then we still have that nearly normal condition. Again, we have two ways we can check that. If your sample size is 30 or higher in each of your samples, you're good to go. But if you have a sample size less than 30, This is where you have to verify that both of our distributions are nearly normal, okay? And sometimes I'll actually provide you with a histogram or a dot plot so that you don't have to go through the work of constructing that yourself. But in some circumstances, you might have to use your calculator, plug in your data for your first sample, do the same thing for your second sample, and then make sure that the two of them are both unimodal and not extremely skewed. We do have this fourth condition. Anytime we're working with two independent samples, we have to verify that they're actually independent. So if we compare one group to the other, we just have to verify that the outcomes of one group do not impact the outcomes of another group. Here is our formula for a two sample t interval. So two sample, again, we're dealing with two samples. T interval, we're talking about a t distribution, and it is a confidence interval. So that's where that name comes from. And you could probably guess what this formula is just based on what we've done in the past. You're going to take your first sample mean minus your second sample mean. Again, we're interested in the true difference between the two population means. And then we have the plus or minus with our margin of error. The t star is exactly the same as what we saw before. Another option is that you can use a two sample t-test on your calculator, and for most purposes, that's going to be just fine. So you don't actually have to go through the process of handwriting all of the work out. Of course, with our confidence interval, we still have that hypothesis test option as well. And typically when we have a hypothesis test for two sample means, we are going to have the same conditions as we had before, so nothing new for our conditions. And almost all the time, our null hypothesis is that our first mean is going to be equal to our second mean, so mu1 is equal to mu2. And just like with proportions, we have a couple of options in our alternative hypothesis. We could say mu1 is less than, greater than, or not equal to mu2. And really what we might be interested in is something like, is the true mean height of 8th grade boys higher than the mean height of girls? We know that in 8th grade, sometimes girls grow taller faster than boys do, so we might want to know, is there evidence that 8th grade boys are higher than, the heights are higher than that of girls? Or we might want to know, is there a difference at all, greater or less than, of the true mean GPA of male and female high schoolers? So one final note I'll say on this is when it comes to degrees of freedom, if you remember for one sample, we talked about how that's equal to degrees of freedom is n minus 1, or your sample size minus 1. When it comes to a two sample test or interval, what you do is you take your first sample size, add it with your second sample size, and then minus 2 from it. So think of it as n1 plus n2 minus 2, and that will give you your degrees of freedom.